Okay, good afternoon, everyone. I hope it's a good afternoon. Usually when I go into class, I say, good afternoon, I expect a response, but maybe, yeah. I'm Eckhard Groll, and I serve as the head of the School of Mechanical Engineering, and I welcome all of you to this distinguished event. We're very, very happy that you come out. So I'd like to introduce what we're doing here, which is the Purdue Engineering Distinguished Lecture Series. And beginning in 2018, the Purdue Engineering Distinguished Lecture Series invites world-renowned faculty and professionals to Purdue Engineering to encourage thought-provoking conversations and ideas with faculty and students regarding our grand challenges and various opportunities in the fields. Besides presenting a lecture, which is the first part of our program today, there's also afterwards a panel discussion, and we encourage all of you to continue to stay and interact during the panel discussion. Right, so it should be a very interesting afternoon. The person who will introduce our speaker today is no other as David Barr. He is the Senior Associate Dean of Faculty in the College of Engineering and also a professor of materials engineering. And before he took on the Associate Dean's position, he served for, I want to say, almost 13 years, right, as the head of the School of Materials Engineering. So it's my pleasure to introduce David Barr.
Thank you, Dan. And it's my pleasure to introduce our speaker for today. So thank you all for coming. Really appreciate it. This is something where we bring in folks that really have interest across the college. It's an opportunity for us to remember that while the schools and the departments we have are very important, the college activities we do that cross between everything from materials to chemical to mechanical to aero is where the strength of Purdue really gets to stand out. And we get to bring in people that can gauge and get excited, many of our students and faculty in all these disciplines. So it's my pleasure to introduce today's distinguished speaker. Babu Chalamala is the Johnson School Distinguished Chair, Professor of Materials Science and Engineering and Electrical and Computer Engineering from the University of Texas at Dallas. Until 2025, he served as a senior scientist at Sandia National Labs. I have a certain personal enjoyment of Sandia because when I was a grad student, I went and worked at the Little Sandia in Livermore. Everybody in Albuquerque said that was like the outpost. And it's what got me started in my academic career. They do outstanding work and many, many relationships and ties with Purdue between Sandia and Purdue faculty and students. While he was there, he provided strategic vision for research areas in grid modernization, energy storage technologies, power electronics, and grid components manufacturing, and led the Energy Storage Technology Systems Department for 8 years. He's a fellow of IEEE, AAAS, and the Materials Research Society. He's a fellow of the National Academy of Inventors. He's a member of the UN Council of Energy for Energy Transition, Engineers for Energy Transition, and he's active across IEEE and MRS, holding multiple leadership and volunteer roles, really helping the professional societies and researchers understand the importance of energy storage. He's a member of the National Academy of Engineering, which is, of course, no small feat. In 2025, he received the IEEE USA Harry Diamond Memorial Award, one of IEEE's pinnacle recognitions. So with that, it's my great pleasure to introduce Babu to give this speech today.
Well, thank you. It's been humbling to come here in this building to present about energy storage. This is my second week as a professor at Dallas. I just started. So this is the first place I am visiting, so I'm very happy to be here. What I'm going to talk is, give you an overview, really, not necessarily deeply technical talk, but present to you where things are in the electrical power system, what are the things that are happening in the grid space, and where storage comes in, and what are the technologies you have, and show you some applications. So it's, give you an overview where storage is the technology and applications are driving the market. And then I'll be happy to participate in the panel session after that. So if you look at the electric grid, things are changing over the last 10, 15 years fairly quickly. First thing you'll see is we've been phasing out the coal fleet really quickly, primarily because there are technologies more efficient, most cost competitive. And most of the fleet in the last 20 years or so, we replaced with natural gas. That's what the replacement for coal was. But over the last maybe 5 to 10 years, we are bringing in a lot of renewables, and that is rapidly growing as part of the mix. And storage is actually relatively new when compared to the rest of the renewables. And that's, it's like solar 10 years ago. Storage is just the new technology that is being introduced into the grid infrastructure. And then after multiple starts in the last 10 years, nuclear is being thought of as being another resource that we can bring up. And there's a lot of activity in bringing SMRs, either as behind-the-meter generation for data centers, or even larger plants coming back online at some point. So that's a new thing for the grid operators to relearn how to bring in new amount of nuclear. Then what people haven't thought about 10 years ago is all the demand that is coming from the data centers. That's completely new. And that is what is driving a lot of the infrastructure growth and the demand, right? That said, we still have a lot of issues to satisfy the demand for additional capacity for data centers, electrification of all sorts, including EVs. And we have been underinvested in upgrading the transmission infrastructure, especially, and to a certain extent, even the distribution infrastructure, right? And besides that, the infrastructure upgrades have been not uniform across. Some places things are happening, some places it's not happening. So that is also a challenge as a country. And then you'll hear about the need for resiliency, how to make sure that the system operates no matter what. And that is becoming a bigger challenge with more natural disasters happening, and you'll see it as you look at the data. And then, unlike many other countries, we have policy which is essentially driven at the state level. Okay? FERC comes in only if you have interstate transmission, just like anything else that the federal government's involved. But energy policy is primarily at the state level. So the PUCs are very different each state. So we have policy bottlenecks in many, many places. There is no uniform policy for all technologies to come in. So that's where we are, right? But you want to take a bigger picture because, not everybody is familiar with the grid. So I want to give you a sense of, how the grid system works. So you have a big interconnected system with some amount of connectivity between the big interconnects. So if you look at the country and Canada to the most part, so you have the Eastern Interconnect, which is Eastern Seaboard, and the Midwest is the Eastern Interconnect. And you have the WEC, which is primarily western part of the country, beyond Rocky Mountains, and the Canadian provinces on the west, and Baja California as part of the same system. And then Texas has its own grid called ERCOT, which is the grid operator in Texas. So you have three large systems, and the Quebec is also connected in the north. So as a whole, we have a system with three you can think of large interconnected systems, but the interconnections are not that much. So there's not that much capacity for connecting the east to west or Texas to the grid. So that's what we have. So we have 3 operating areas, and then as a system, it's roughly about 1,300 gigawatts of generation capacity, and the base load is somewhere in the 850, and the summer peak is 1250, right? And then you got things like data centers coming, so the numbers are changing very quickly. But that gives you a sense. We have a terawatt grid. So how do you operate a terawatt grid? How do you make changes on that scale is what we are looking at. And we produce roughly about 4,000 terawatt hours of energy in a year. And the thing is, we deliver power at 13 cents a kilowatt hour. And you might ask, that's pretty cheap. Yes, we provide reliable power at a very low cost. But 13 cents has significant change in the last 5 years. It used to be 10 cents. So we went up by 30% in many ways. So cost of energy is increasing. And then how do you balance this whole system? So we have a number of balancing authorities. Essentially, you can think of local balancing authorities in many places, large load centers, and many of them across the country. Eastern Interconnect, 31 in the US, and 5 in Canada. Western Interconnect, similar number, then ERCOT and Hydro-Quebec. So you have a complex system. And the goal is to operate the system reliably and provide reliable power no matter what at a very low cost. And that too based on a model, not one entity. We have 3,000 utilities in the country. So it's a very diverse system. So how things are changing is also important to see. So if you look at what we have roughly 3,000 generators of some sort. Anything that is more than a megawatt of generation capacity is considered a power plant by EIA. So you have about 3,000. It's a lot of entities, and all these entities are connected to the grid. And if you look at the bottom graphic, you'll see what capacity is being retired, what capacity is coming online. Over the last 15 some years, most of the capacity that we retired is coal. That's about 250 gigawatts of coal. And a lot of us replaced by natural gas. And we are adding a lot of renewables, primarily solar to a large extent, and some amount of wind. So that's what the mix is in the system. And as you look out to 2050, we still have a lot of natural gas, but the role of renewables is going to change. And we have policy framework, that is evolving, changing, but the drivers are the same. What is being built today, significant amount of it is natural gas right now, as you can see. What is being built next year? 50% solar. And that's what we have, and we are still building gas. So the drivers for renewables are continuing. And you see the global picture, not very different, and somewhat dynamic, actually, much more dynamic. In the last 10, 15 years, we brought up over terawatt of wind capacity globally. Solar is more than 1.5 terawatts now. That crossed 1 terawatt in 2021. We're bringing a lot of battery capacity, and that's, as you can see, the pace is really fast. And by looking at the color, a lot of it is happening in China, and followed by Europe, and some amount of storage coming into the US. Same story in EVs. Lots of EVs coming into the market, and a lot of it is red. And it's all driven by in China, and we are slowly picking up, but amount of EVs in the US is fairly small, modest at this point. So global picture is towards renewables, towards electrification of the transportation fleet, and how do you operate systems with a lot more renewables is the key for the system. And this is not really driven by policy alone. Okay, if you look at the numbers, end of the day, does it make sense financially? Does it have the capacity? The project bankable, right? So the number shows you that, right? So if you look at the graphic on the right side, you'll see how prices of renewables have been going down compared to combined cycle gas, right? Now they are at parity, okay? The only challenge is making renewables firm. Solar is not firm resource. Wind is not a firm resource. So how do you make it firm is one of the challenges that we have, okay? That's only one part. So if you look at the generation side, a typical 13 cents or so, or 10 cents, you have 4.5 or 4.6 cents in the generation, and the rest is transmission and distribution, okay? So you have, most of it, half of it is generation, and the other half is T&D, right? It'll continue to go, we can continue to bring the cost of the generation down. We still need to invest in the transmission and distribution infrastructure, which is expensive. So the bottom line is, things are happening because it's cost competitive. And as I mentioned earlier, the grid edge is where the action is, right? Anything behind the meter is the edge, okay? Data centers are behind the meter to a certain extent, even though they are large assets, but it's still a behind the meter asset in many ways. Transportation fleet, projections were at one point, 5 years ago, people thought we'll have 30% of the fleet becoming electric by 2030. It's not happening that fast, but longer term, it's going to happen. It's just a matter of time, right? And that's all grid edge. We're going to bring significant amount of capacity need to charge EVs at some point, and that's the grid edge, and we are not ready for that. And increasingly, the loads are becoming electronic, so DC loads, right? And the system is all, bulk system is all AC. And the DC loads are power electronic centric. So the energy conversion is power electronics driven. And that's going to be more and more, right? And then when we use the word DERs, we are talking about assets that are going to be available, that we can monitor, control in a distributed fashion. There's a lot of intelligence, computational stuff, and communications. So the system is very intensive with communication controls. And that's going to get more and more complex as you operate. So operationally, you're trying to control millions of devices in some sense, right? And balance in the system. Then you have to be able to protect it, right? If you're bringing in all these assets, how do you provide the protection for the system is also key. And cyber is becoming more and more a challenge and a need because every DER device has some kind of a converter or an inverter with a telecom interface to control. So you have a cyber aspects coming in. And then you're beginning to think about the nuclear, okay? That's a new thing. And data centers is one thing that is driving the growth. And if you look at the middle chart, comes from the FERC. FERC was making projections 2 years ago, and the numbers was, projection for 2025, and forecast was 23 gigawatts, and then 2024, that became 128. So the numbers are changing really quickly. If you ask somebody a couple of years ago, do you see a data center with a gigawatt capacity need? The answer would have been, no, you're joking. There won't be a gigawatt data centers. Well, they're real now, okay? I mean, the two big gigawatt data centers, they're under construction in Mississippi and Louisiana. So we are integrating data centers at a very large scale. These are, large assets. And these loads are not base loads. These are lumpy, localized. And there's lots of aspects how to operate the data center loads. How do you manage? So that's coming to the grid very, very fast. It's mostly localized in 6, 7 places at this point. But those are all places where also you have infrastructure problems, like Northern Virginia. You can't bring transmission. It takes 5, 10 years to bring transmission. So we have issues even to provide the capacity needs for the data centers. So the different models are evolving. How do you provide capacity? So data centers is the other thing that is happening in the grid. As I mentioned, power electronics is going to be the central for all the things, okay? You don't see it as much, but each one of us are carrying, 3 or 4 converters in our pockets and bags, right? And that's going to get more and more. So conversion from big machines to, power electronic converters will happen very quickly. And right now, in some sense, we get maybe 30% of all the electrons get converted in a power electronic converter. And as you go to a deeply decarbonized system in the next 20 years, we probably goes close to 100% power electronic. And the grid guys don't know how to operate a fully power electronic centered grid. And the power electronics hasn't scaled up. Most of power electronics is, they're still low voltage devices. How do you start getting the voltages to 800 and to the distribution level, okay? So there needs to be a scaling of power electronics to higher voltages, and that's beginning to happen. So with all these changes, maintaining the system reliability is one of the challenges a typical operator is going to have. I mean, you would have seen the California duck curve, right? The California duck curve is basically, a lot of solar capacity comes during the daytime, and evening you need to bring in anywhere from 12 to 13 gigawatts of capacity to when the solar is gone, right? So that is the duck curve. Now that's happening in every place. Now there is a Texas duck curve. So pretty much every state has a duck curve. So And managing that level of uncertainty and bringing that level of capacity every day is one big challenge, and that imposes issues on the reliability of the grid. Then as you move towards resources which are not big synchronous machines, providing inertia is also one issue. And most of the assets we have in the distributed assets, they're not grid forming, they're grid following, which means as soon as the grid is gone, you don't have the inertia, right? So how do you get these assets to be grid forming is also one thing that is happening, but not there yet. Then all the renewable resources also happen to be for solar, primarily in the southwest, or wind on the coast, which nobody wants to build. But there are bottlenecks to bring that much capacity from those places. So transmission hasn't caught up. I mean, for example, Texas has most of the wind in the western part of the state. They're beginning to build transmission lines now. So we have transmission infrastructure issues to bring the capacity. You also hear about resiliency. I mean, if you were in Texas a few years ago when they had the deep freeze, well, that's a resiliency event because we weren't planned for it, but that level of failure. And if you get another polar vortex into Texas, is the system ready for something like that? Well, anybody's guess at this point, right? So, and the reality is, if you look at the NOAA chart, whether you believe in climate change or not, the number of events which cost more than $1 billion have been going up and up. And for every dollar, we spend about $150 billion a year as a country on getting the system back up and running after failures. And for every dollar we spend on procuring power, we spend half a dollar to get away from the failures. So resiliency of the system is not what we want. But there is no service that's called resiliency. We think of reliability, but not resiliency. So system is not robust enough to handle all the problems that we're getting. So that said, I think things are happening in some interesting ways. People would think Texas there won't be any renewables if you keep people asking. Well, Texas connected 39,000 megawatts of wind and 25,000 megawatts of solar. And most days, nowadays, sometimes they have 80%, 90% renewables operating during the daytime. And they also brought in close to 10,000 megawatts of storage. So that gives you a sense. We have policy-driven place like California, which has similar numbers, and a fully deregulated market like Texas has similar numbers. That tells you what is driving is economics here in both the markets, right? So with all that, with so much of renewables coming into the mix, and we're not even talking about the electric vehicles at this point, and not even data centers, the operators need some flexible assets. One of the flexible assets, as you can see, that why Texas deployed close to 10,000 megawatts of storage, California plus 10,000 megawatts of storage in the last few years, is because they provide an asset which is flexible, bidirectional, right? So that's where storage comes into the mix. So what do we have in storage? Okay. If you look at what we have from a terawatt grid operational point of view, if you think of a storage device as a generation asset, it's roughly 0.5% of the capacity. It's very small. And even out of that, close to 30 gigawatts is what we built in the 70s and 80s when we were building the nuclear fleet. So, and then we brought in maybe 30 gigawatts of 4-hour batteries, 120, 130 gigawatt hours of batteries in the last few years. But that's only 30 minutes of ride-through. So the amount of storage we have is fairly small, okay? It's picking up, but we are pretty far from where we need to be. I mean, if you look at the big picture, we have a terawatt grid. Even if you think of 1 hour of storage is 1 terawatt hours. And if you want to decarbonize the grid or bring in a lot more renewables at a much higher level, the amount of grid storage you need is going to be much more larger, okay? So what do we have? So we have a range of technologies. If you're doing short duration storage, power applications, demanding, and you have technologies that can do it. And then longer duration, we still have a gap. I mean, if you were to ask today what long duration storage we have today is primarily the pumped hydro. They can do 10 hours, 20 hours, most places. Batteries, typically 4 hours, right? So energy applications are the ones which are hard on technologies, right? And those are the markets needs the lowest cost. And those are the things that we need large amounts of it. Power applications like regulation and other things, those are, I think, are taken care at this point. We can handle, right? So as we look at what storage we have lots of battery technologies, and then longer duration, we are looking at pumped hydro and other technologies at this point. So what we have deployed in the last few years, so you can see, most of what is coming in the pipeline is all hybrids. If you were to ask 5, 6 years ago, a lot of the storage deployments was for regulation market in PJM and CalISO, all those things, right? That market is more or less saturated right now. So now all the projects that are being deployed are solar plus storage hybrids, standalone storage, and some amount of storage plus wind. So it's all towards hybrid systems, and firming up renewables is where storage is getting deployed. And where it is, I think, as you can see, it's in CalISO, ERCOT. Those are the two places where most of the deployments are happening, and that's where we have right there. So, and what we have, I think, I mentioned pumped hydro. Pumped hydro, you can build large projects, locational specific, and they're more large-scale engineering projects. So they don't have the modularity to build a small system or a medium-sized system. You don't have that. And those projects tend to take many, many years to get the permitting and construction and all those things. So we haven't built a pumped hydro project in, 30 years now, right? So what we have is batteries. So I'm going to talk about primarily batteries. I'm not saying that, pumped hydro and the case are not going to be happening, but some countries, they're happening, but not here. Here is mostly batteries at this point. And within batteries, it's all lithium-ion batteries, okay? And that is becoming mature as a technology. And most of the grid operators over the last 5, 10 years have learned how to deploy lithium-ion batteries at scale. So there is bankability things. And there are other things on the horizon. You hear about flow batteries, metal air batteries for longer duration storage. And those are happening at maybe pilot scale at this point, not really big. So for shorter duration, essentially you have lithium is the technology of choice, okay? And at this point, anything else is an alternate. So I'll discuss, what are the things happening in the lithium-ion battery industry and give a sense of where things are with the rest of the things. So for most part, ever since Sony commercialized lithium batteries in 1992, it has been the technology of choice for mobile devices. And we learned how to build large-scale manufacturing of lithium-ion batteries, consumer electronics, and computing. What drove it for nearly 20 years? And the same technology platform is the technology for EVs. And it is the EV industry which is driving both R&D, technology improvements, manufacturing, not the grid. Grid is actually getting benefited from what is happening in the EV industry capacity. But that said, there are a couple of different things. EVs, form factors, roughly, large battery packs, each about 50 to 100 kilowatt hours, and well engineered because you need to have a battery pack which is thermally well managed, liquid cooling, and all the things. You take the same technology base and build slightly lower cost systems for the grid. You don't have the same level of engineering. You basically, in the grid side, you make them in modular 19-inch racks and put in containers, 20-foot or 40-foot containers. So it's slightly different, but base technology is the same. The only difference is in the EVs, power is really important. So they tend to use NMC, nickel manganese cobalt, or NCA, which have much better energy and power capacity. Grid started with the same technologies a few years back, and now as lithium iron phosphate, which is the slightly lower energy density, but has a better thermal profile, has become the main technology for the grid. But also, I think it's becoming the technology for EVs, mainly because it's cheaper in many ways. So, and lithium batteries is not just one technology. It's a family of electrochemical systems, right? And you have the positive side, you have the metal oxides, have LCO, NMC, NCA, and then phosphates, which are becoming the main driver for the grid applications. And the anodes, you have the graphite for the most part, okay? That's what drives everything. And then we're trying to get better capacity and various alloys that can give you higher energy capacity on the negative electrode, and silicon alloys of some sort, 10% silicon, 20% silicon at this point. So those are the material systems we have. So what we have, state of the art, 250 watt-hours per kilogram. That's what you get. So you take cells with that kind of energy density, build battery packs, and build systems based on small cells. So you want to build a megawatt-sized system, you're talking about 8,000, 10,000 cells, right? So it's an integration challenge. So it's not just about battery technology. With increasing energy density for what we want, because you want to have more energy dense, so the packs are more dense, we have safety issues. The safety issues with the lithium-ion battery systems at large scale is real. And what is driving here, as you can see here, a lot of the manufacturing capacity came online in the last few years, okay? Just basically barely 5 years, you can see all of it. So we have close to 4 terawatt-hours of manufacturing capacity for lithium batteries globally. Most of it is in China, and we also brought in a lot of capacity in the last couple of years within this country, driven by auto majors. And right now, I think there is significant amount of overcapacity, and that's helping the grid storage industry, really. So where is this capacity going? If you look at it on the right-hand side, most of the capacity is EVs, and a small amount is grid storage, and then consumer electronics a little bit, right? 20 years ago, it would have been all consumer electronics and computing. No longer the case. So it's EVs which is helping the energy storage industry, really. The only differentiation is, the battery packs are very different for the EVs on the grid, and the size and the format. So LFP is what drove things in the last few years. The other thing you see is, we have learned how to make these things really cheap, okay? And if you were to look at the lithium battery industry, it's commodity, okay? There is no real differentiation between batteries from a company X and a company Y. They are the same, slight variations, really. And what drives is, what is my cost and per kilowatt hour? And that cost has dramatically came down in the last 5, 6 years. Now it's almost like cell level costs are close to the bill of materials. So nobody is really making money in many ways, right? And you bake the cells on battery packs. So at the pack level, you come down to the point where these systems are cheap enough to deploy for most applications that you need, right? So where the storage is going, you can see battery storage for the grid is on the top, and that's where our current capacity is. And over the last maybe few years, I think the engineering is becoming standardized. A few years back, people were building plants. They were engineered to be individual plants. That's not the case. Now we basically design a 20-foot or 40-foot container fully ready to go and interconnect with the grid. All the app developer has to do is put the pads and bring in grid connections, right? So things have become fairly modular, standardized engineering practices, right? That helps projects to be bankable. So we are deploying things at a very fast scale because we know how to build these things as uniform objects, right? The one area which is still concerning for many people is safety, okay? The lithium batteries still tend to have safety issues, but even those, I think, are being addressed very quickly. So what is the outlook for lithium batteries, okay? Despite what you might hear from people from different parts of the energy storage industry, I think, right now, that is the technology. And there is a clear pathway for lithium batteries to be the technology for many, 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 many years. Not only just because it's a driver for EVs, that's where the investments have been, that's where the scale has been, and product platforms are becoming very mature very quickly, right? So, and you can build projects without too much worry about bankability, reliability, operational reliability, and all the things, right? That's a short term, okay? And when you have a technology with a 3 terawatt hours of manufacturing capacity per year, you incrementally keep on improving. So we are getting a lot of improvements, even though they're incremental, and that will result in both price performance. Cumulatively, that'll be significant change in the next 5-10 years. So short term, I think, the areas where things are going to be, improving are in the packaging. How do you thermally manage these things? How do you deploy these things, right? Longer term, we'll need to bring in safer electrolytes, okay? That's work both the EV guys are doing, big guys are doing. One aspect, how do you improve the safety profile of lithium batteries is, can we have better electrolytes? That's where the safety issues are. I mean, we can address safety at the materials level with going to LFP, but electrolytes are what makes them less safe, right? Longer term, at least for the EV guys, solid-state batteries, lithium metal, but for the grid, probably not, right? They don't need the same level of energy density and the power requirements. And then far future, maybe lithium-air batteries, and then metal-air batteries, but longer duration, there are other air batteries that are coming into picture. Lead-acid, early days, used to be deployed in demonstration projects for grid storage. No longer the case, okay? I mean, there are a few projects here and there, as the technology is actually quite expensive compared to lithium-ion at this point. So there are no projects being built, and not likely to happen anytime soon. So UPS is one technology right now. Lithium-ion lead-acid batteries have a dominant role, and that will probably stay that way because of safety issues of bringing lithium-ion into buildings. But UPS is one area. There has been improvements in improving the cycle life of lead-acid batteries, especially on how do you bring about high carbon electrodes. But cost has been the challenge. Can you make these things much cheaper so that we can get the kind of cycle life we need? That hasn't happened. So both cost and the general technical challenges of lead acid, I think, it limits the deployment in grid storage. And then you hear about flow batteries. And flow batteries have been exciting for many, many years. People thought flow batteries will take off because they provide the separation between energy and power. But it's slow going at this point, okay? Vanadium flow batteries is 50-year-old technology developed at the same time as lithium batteries in the 70s, right? Few things are limiting. They are not at scale. You don't produce these technologies in the terawatt hours of manufacturing capacity. I mean, the largest flow battery companies are, maybe do 300 megawatt hours per year. You don't really the scale. Then on top of that, you have a system with a 30 watt hours per liter, which means, I need a large footprint, and steel and plastic cost money. So even though it's mostly electrolyte, overall system costs money. So that part, balance of system, is expensive. So, and some of the chemistries like vanadium, they have been commercial and projects are being built. And as you can see, that's one large project in China. For example, Bronchi Power built a 400 megawatt hour. That's the second 100 megawatt hour project. So people are building large projects. Are they cost effective to compete against lithium-ion? That's the challenge. And they are not bankable at this point. At least commercial projects are not being built in the US. So longer duration, they can store long duration. I think, flow batteries will play a role, but there is no market for longer duration right now. So what does the companies in the long duration, the flow battery business, how do they survive until the long duration market comes on is one of the challenges. So it's mostly pilots at this point. Then you hear about sodium sulfur batteries. This is a technology developed in the 70s by Ford Motor Company and then moved to Japan. For many years, this was the most bankable projects for industrial energy storage. And GE brought in a manufacturing plant several years back, and they closed it. And NGK in Japan was the only company which was commercially building systems based on sodium batteries. And they've done fairly well over the last 20 years, and almost like 5 gigawatt hours capacity in Japan. And 2 weeks ago, NGK decided, we're not going to make these anymore, okay? So the last big manufacturers, mass batteries, decided to shut down, okay? Why? They haven't been able to bring the cost down below $300 some. I mean, that's rough number I hear, right? And now the competition with the lithium-ion, much cheaper than NAS batteries. So the last NAS battery company decided to shut down. So there are right now small-scale manufacturing, nothing at the level that NGK used to do. So even though has proven to be stable and scalable, deployable, again, this is one technology from a cost point of view, performance point of view, I think, having a challenge. Then you hear about all the zinc batteries, okay? People talk about low-cost, earth-abundant materials. Yeah, zinc is a cheaper system, okay? Lots of zinc chemistries, nickel metal hydride, nickel iron, zinc manganese oxide, all those things are systems that from a materials point of view, they are cheaper, they're abundant, but they are not at scale. So a lot of the zinc chemistries, I think, are not at the scale, and people are trying to make them work. For example, zinc MnO2, which is your alkaline batteries, they're now finally rechargeable, but they're not at scale to compete with lithium-ion, okay? Even though on a kilowatt-hour basis, the bill of materials for zinc MnO2 is probably $18 or $20, but you have to bring those systems at scale. But that's interesting areas of R&D continuing on the zinc batteries. Sodium-ion as a potential alternate for lithium-ion is promising. And will that be the alternate for lithium-ion? I have no idea, okay? And based on history, I think, if a technology entrenched like lithium-ion today, will a replacement happen? Likely not, right? Because what sodium provides that lithium can do, right? Supply chains maybe, but supply chains is not what is driving the only thing, okay? It's established technology, scale, manufacturing, all the other things that go with it. So for a new technology to come in and replace an existing technology, it's a tall order, right? But some companies like CATL and others are pushing sodium-ion as a potential alternative. We'll see what happens, okay? Solid state, EVs are driving in, but long way. And then longer duration. As you look at the grid, deeper decarbonization, a lot more renewables in the next 20 years, we do need longer duration storage, 24 hours, maybe days, weeks, right? We don't have anything other than that, okay? I mean, if you look at what we have today, is 3 days worth of gas in the lines, right? That's your longer duration. What equivalent do we have in batteries? None, okay? Once we get close to maybe, 80% renewables, that's when we start looking the need for somewhere in the 100-hour plus energy storage, longer duration storage. And many of the companies working in this domain are targeting that market. And what are those companies? You would have heard about iron air batteries, zinc air batteries of some sort. These are all based on materials which the active materials are cheap enough, $1, $2 a kilogram. And so you have potentially low-cost technologies, but they have their own issues. For example, if you look at the zinc air, round-trip efficiency is 60% at best, right? Air cathodes don't perform well. So we have foundational issues on air cathodes. And then if you have a technology doing 60% round-trip efficiency, that's a big challenge to operate in the grid, okay? And you're basically losing 40% of the electrons. So, and even worse for iron air, I mean, they're 40% efficient. And the balance of plant is humongous for a gigawatt-hour plant, right? So these technologies have the challenges. On top of that, if I have an asset which is 40% efficient, can I participate on a daily basis in the grid? No, right? So these are going to be reserve devices. And is there a market for that scale? Or do I keep my existing natural gas plants operating as the needed capacity when I need it for 5% of the time? So that's where we are. That said, it's not all about batteries. Batteries, or at least the energy storage device, is only a small part of the energy storage system, okay? So if you look at this graphic from Bloomberg, you'll see what all the different things come together to make a battery plant, right? You have storage devices, then you bring in power electronics, containers, thermal management, most of them have air conditioning of some sort. And all the power electronics and the grid interconnect. And that's where the real costs are. Even if I have free batteries or free energy devices, it's still going to cost me, right? And even though the battery side of things have been significant cost drops, the system side, balance of plant, we haven't gotten the same level of efficiencies. And that comes as we build more and more in much larger capacities. Then safety. Even for technologies which you think are safe, there are still issues. Thermal runaway is the thing for lithium-ion batteries. But if you look at this graph, the number of events, even though we are building close to 40, 50 gigawatts now, the number of safety events have been dropping. So we are learning how to build these plants much better, right? That's one. So we continue to improve on safety. Can we bring these devices to the buildings, inside the buildings? Maybe it might take some more time, but we are there, right? And if you think about flow batteries, people think flow batteries are safe. It's aqueous electrolyte. Nope, that's not true. I mean, there have been lots of flow battery system failures that caused significant issues, either gas evolution or spill, right? So they have their own issues. Every technology has safety issues, and the goal of engineering is how do you make these systems to be more reliable, not perfect, but more reliable, more safer. So one way to make things safer is to have standardized engineering practices. And the standards process tend to be slow, okay? It's slow, boring, but that needs to happen. And that is beginning to happen. What are the drivers? Well, we had major fires. So people asking for, okay, are you in compliance with all the existing standards, okay? So it's a regulatory practice. So that is beginning to happen now. Now, if you look at, is people complying with, NFPA, 855, all the things? 5 years ago, probably not. Now all the plants are getting there. Interconnection, same thing, okay? Now people have to comply with IEEE 1547, if it is the DERs, or I'm connecting my storage device to the transmission grid, well, 2800. So these are new standards. So standards make things safer, okay? And that's the industry is moving that direction. Still inadequate to the most part, I would say, okay? But because it's a regulated practice, unless somebody asks, okay, you shall do it, standard doesn't become a standard, so. Then people say, okay, storage can do a lot of things for in the grid. Well, it can do a few things well. And those are the only projects that are bankable, where markets exist, okay? So if you look at, my old group at Sandia did a report 15 years ago, okay, looking at all the storage can do. So I listed 64 different applications where a storage can participate. Well, the reality is, for the most part, it was frequency regulation for the first 10 years, right? That was the only market where you could bid your device. Now we have renewable firming is happening. We are beginning to bring storage into the transmission grid. Transmission projects are happening, right? So some of the large, but there's still a small segment, right? And then solar hybrids are happening. So their markets are opened up, but not all of it. And also devices can do all the things at the same time. So it's kind of a historical evolution. If you look at the graphic here, Hawaii, that's a 15-year-old project. So 15 years back, 6 megawatts of storage device was just big, right? Well, 8 years later, California had Aliso Canyon fire, and they lost a lot of natural gas capacity, and the California utilities needed to bring a lot of new capacity. They deployed lots of peaker plants, right? Peakers became common, peaker replacement. Well, now you look at it, on the bottom, there is the close to 4 gigawatt hours, 3.3 gigawatts of storage, all to work with a 875 megawatt solar plant. So you're building plants at 4 gigawatt hours, right? So engineering went from 1 megawatt 10 years ago to gigawatt. Now we can safely, reliably do gigawatt. So we have come a long way within a short time, right? And resiliency, this is a mobile device. We can bring in a few megawatts of storage to a site where if you need emergency power. So applications are opening up, things are happening, and that will continue. So what are the things, still not mainstream, it's kind of a still niche. Now we still need to improve cycle life. The batteries are oversized right now, so that they'll give you warranty for X amount of years. Okay, that's because cycle life is not there. So can we dial the cycle life by a few thousand more cycles? Then I get a few more years, right? That's one area. We still don't have long duration storage. Okay, we still need to improve safety. Okay, that's reliability, safety are keys. And then we are scaling small devices for the most part, 10 watt hours, maybe 100 watt hours for prismatics to megawatt scale systems. So we're building small devices to large complex systems. So we don't have real scale at the device level. Is it possible to have larger devices so that we don't have to do so much engineering to build larger systems? So that's one. We have robust supply chains for the most part. They're not global. Do we have domestic supply chains for all the things we want to do? Then on top of that, at some point, we have end of life for all these devices. Do we have recycle and reuse? And that part is just coming now, okay? It hasn't been profitable to recycle as much, but I think, once we have volumes and the recycling and reuse, it'll become real, and those businesses are taking off. Project finance, still you need to handhold a lot to bring a project to life, okay? Standardization of equipment processes. I mean, if you look at the solar industry, what drove significant cost systems, I think, standardization of other things. And the same thing is happening in storage. And then grid operations. We don't have all the good tools, okay? There's a lot to be learned on how to help the grid operators on how to use storage. So those are the broad things. With that, I thank you.
We have time for a couple questions, and then we will do a breakdown. Wait for the mic. That way the audience gets to hear your questions too. So I'll start with this second.
Very nice. Very nice presentation. I enjoyed coupling grid with batteries. Now the grid system in US is 140 plus years old. If you make more and more energy with renewables, do we have to change the grid system or build the small microgrids locally?
Well, I think, the grid is fairly robust. I mean, there are infrastructure which is aged, but we've been replacing a lot of it, right? So we don't have to rebuild the grid per se, right? You're asking a slightly different question. Do we go towards a paradigm where we have millions of microgrids, right?
Yeah.
That's a good way to look at it, but I think, we'll still be tethered to the bulk grid for the most part, because, we need the reliability of the bulk grid, and that provides the backbone. Will we have a lot more DERs? Yes. But they won't be the primary, because essentially because building a large plant is a lot more cost effective than building a lot of small plants. That hasn't changed.
That's true. Thanks.
Babu, very nice overview. A few years ago, lithium-ion was the holy grail of all batteries. What's the latest on lithium-ion?
Well, air electrodes are not easy to deal with. It could be lithium-ion, zinc-ion, iron-ion, same problems. My air electrodes are difficult, not efficient.
Have we given up on them, or?
No, people are not giving up. I mean, there are several companies working on air electrodes for iron-air for long duration storage, zinc-air for long duration storage, lithium-air for other applications, right? Not big, but mostly for high energy dense applications. So people are working on it. If you need only a device for shorter durations, those are available.
Thanks.
Do we have one last question before we do this split?
So you mentioned that the safety regulations in the industry are pretty reactive in the standards that follow them. Do you see potential for upcoming regulations surrounding fire safety with lithium-ion to cause a shift to other maybe equally as unsafe chemistries like zinc, but that are not specifically fire unsafe? Do you see potential for a diversion in spite of the established supply chains for lithium-ion?
Well, I think, people are learned how to build plants much more safely. So if you look at, EPRI has a database who monitors failures at large plants. Things have been going down. Same thing happened in every country, right? Now we have an PA 855. We know how to build batteries much better. We engineer at the pack level. So every level, things have been improving. So safety profile is way better than what it was 5 years ago, 10 years ago. And then, is there compliance in all the places? Well, I think, it goes to the PUCs. If the PUCs say you shall do it, it becomes part of the standard. And I think, the standards have caught up finally. So, thank you.
Again.
Well, thank you.
Not completely done yet. So it's now my distinct pleasure to provide this plaque to you in honor of your talk today, which we enjoyed very much. So this is presented to Babu Chalamala in recognition and appreciation of your contribution to the Purdue Engineering Distinguished Lecture Series. So thank you very much.
Thank you.
Yeah. And I need to